It's probably good to tell everybody who we are. So you heard my name, I'm Fyl Pincus. So but the question is where we're coming from, because background always gives context. So my PhD, a long time ago now, at Berkeley, I worked with Charlie Cattell on magnetism. So most of my career, I'll say the first half was all in, let's say, traditional solid-state physics. I worked on magnetism. I had a buddy who was a postdoc when I was a graduate student by the name of Dejen, so we became so I worked a lot with him on superconductivity, liquid crystals. I also did a lot of work with another guy you might have heard of, Alan Heeger, on correlated electrons and conducting polymers. So I sort of have more of a solid state background, and only started, let's say in the second half of my career in soft matter stuff. So, and that background will probably come out in some of the lectures. I know, so I have this funny trajectory. I like to also emphasize a few things that Leo said. First, asking questions. I love questions. I'm not going to use PowerPoint. This will be all, think of these as informal talks. So if I say anything you don't understand, or if I use jargon that you don't understand, just ask questions. As Leo said, if you don't understand it, somebody else probably doesn't understand it. And it's more important to be coherent, to understand what we're talking about than covering the material. One of my old mentors from UCLA, Ted Holstein, always used to tell me that when you go to a talk, you should listen to get something out of it. If you don't understand what the speaker is saying, it's his job to make you understand, so ask. So either ask or get up and leave, because the only thing you have in life is time, okay? So you don't want to waste your time just sitting and not following. The other thing that I wanted to say about these kind of schools, the first school that I went to of this style was actually in France, where there's a set of schools in Brittany called Begarou, a place with a French sailing school, and that was the first time I had experienced this, maybe 20 years ago now, and I realized that these things are really good. And the thing that's best about these is not the material, and it's a little bit what Leo said. It's the fact that you guys represent a finite fraction of your generation in the world that's working in this kind of area. So that means the contacts we make with each other you'll stay with you for the rest of your life. So those kind of interpersonal relationships are the main thing that comes out of these kind of schools, in my opinion. And I saw that in Begarou, and I saw it in the two others like these that I was over here. And by the way, Leo does a tremendous job in organizing these things. I mean, it really works well. It doesn't feel like he's doing much, but there's a lot done behind the scenes, I'm sure, Leo and the Anders group. Okay, so what I'm supposed to talk about is stuff that you all know. Okay, I'm supposed to talk about what are the fundamental forces that play a role in, let's say, in soft condensed matter, or more specifically in polymer physics. And so my going in point is this is something everybody should know. And I'm not trying to instill on you, say, theoretical methods or computational methods. It's more how to understand the physics that's going on. I mean, you could figure out, do homework problems and figure out how to do the calculations. And again, everything that I'm going to say in these three lectures, you should kind of know. I might say them in a different way, when you see them, and because the way things are done in textbooks are not necessarily the only way to do that. But okay, so okay, now the other thing is that even though I'm talking about stuff that you're supposed to know, it doesn't mean these things are well understood. To a large extent, everything that we talk about, you don't have to probe very deep before you realize there's something that's not quite kosher. Things are a little not as good as they sound they are, or they're more complicated. And so there's a lot of like fundamental science yet to be done, even in these kind of simple stuff that I'll talk about. Yeah, so I'm gonna give these like 3 lectures, and roughly speaking, they're going to be in the following way. They'll be what I call, if I know how to spell it, ubiquitous forces. Things that are always there, whether you like them or not. There's going to be one lecture on mainly on electrostatics, and one lecture having to do with things like hydrogen bonds, hydrophobic effect, things like that. Okay, but then probably I'm not gonna be packaged very well, but that'll be the rough order. So let's start at the beginning, and everything or most things you're going to hear this week falls under the rubric of soft matter. And so soft means kind of squishy. My friend Bob Burgeono calls soft matter sludge physics. So that's another good description for Mike. And so squishy means that you want to talk something about an elastic modulus. And if you look at an elastic modulus, I'll call it G. It's, as far as dimensions is concerned, it's an energy per unit volume. So for me, it's some kind of temperature divided by some length cubed. Those are the dimensions of modulus. And if you look at ordinary hard materials, the characteristic temperature Tc may be something like 1/10 of an electron volt. By the way, another thing that my thesis advisor, Charlie Cattell, always insisted upon for us is physics is numbers. You always have to put in numbers. And we'll see that over and over again. It's important. So that's about, let's say, 10 kT. For me, Boltzmann's constant is always 1. Okay, everything. KB, I always work in KB units with Boltzmann's constant. And for hard matter, L, let's say, is in the order of an angstrom, 10 to the minus 8 centimeters, and you can compute a modulus.
What is TC?
Some characteristic thing that represents the interactions of the system. Transition temperature, the cohesive energy, the melting temperature of a material, anything like that. 10 or 100 kT. T means room temperature. That's for hard matter. For soft matter, the interactions are the same. So it's still Tc, but for soft matter, L is about 10 times A, where A is about an angstrom. So for soft matter, G is about 10 to the minus 3, the modulus of hard matter. So the whole issue in hard and soft is that length scales are bigger. That's pretty much what distinguishes hard and soft matter. I know Michael doesn't like it, but it's right.
Isn't T different in soft matter? Is KT or
it's the same thing. The interactions are all the same.
Well, in hard matter interaction is the curvature of the potential typically you're thinking about.
Well, you're talking about, I'm just talking about more crudely, transition temperature.
It's the same.
100 kT, 10 kT.
But for soft, it would not be 100 TTO of a length scale. It would be TTO.
Yeah, the interactions are the same. It's just that the objects are larger. So soft matter has to do with nanophysics.
But in hard matter,
So he'll argue with me.
Yeah.
I'm right, he's wrong.
I heard
He can defend himself later.
in hard matter, one would think the typical interaction would be covalent bonds and
Something, well, I'm talking about even something weaker than that. An exchange interaction in a magnetic material, a hydrogen bond, something of the order.
Is not what creates
Yeah.
the elasticity, it's what creates...
I'm just trying to be very crude. Okay. But the main issue is size. That's what the emphasis on. The main issue is that for soft matter, you're dealing with fundamental objects that are large. So let's talk a little bit about energy scales. Since we're talking about that. So for condensed matter physics, condensed matter physics in general, the fundamental energy scale is an atomic energy. It's an atomic energy, which is of the order of electron volts. Okay. The next smaller energy is of the interactions, the ones that I try to list here as Tc. And these may be of the order of a tenth of a volt. Okay. The other interaction that is important, at the next level, I'll call it E3, is entropy, that is temperature, and we're dealing always with around room temperature, so this is of the order of 100th of a volt, okay? And that's the hierarchies of energies that we're dealing with. Now, if most of condensed matter physics in general, hard and soft, we don't worry so much about that energy, because the atoms that we're involved in, especially in soft, are pretty much fixed objects. In hard matter, maybe you're dealing with it a little bit, and so in the same sense that we don't have to worry so much about the integrity of atomic species. It's in the same way that in hard condensed matter, we don't worry about integrity of nuclei. We don't worry about the strong interactions and things like that, because we're not doing things where that's changing. Okay, so we're not thinking too much. Most of the action that we have is down here, between the interactions and thermal energies and entropy. Okay, the players that we'll talk about, what are the objects that we're dealing with, I don't want to spend much time on that, but typically in soft matter, we're dealing with colloidal systems, which are something like solid materials. They don't have to be spheres. For example, like suspensions, for example, of gold in some solvent. Or we're dealing with emulsions, which are immiscible liquids, two liquids that don't mix, so they form liquid droplets in a solvent. Or we may be dealing with foams, which is gas in a solvent. Miscible gas, okay. Now, in these lectures, I mean, not my lectures, but in the ones that you'll hear, there'll be a lot of discussion about larger objects, which you know about, polymers. And I won't say much about it. I think, sure, you'll say a lot about it. But you know, for a physicist, the first thing of a polymer is you just take little beads that are struck together by universal joints, and that would be the first simplistic picture of a polymer, where these beads may be any size, but typically may be, again, of an atomic size, okay? And these things could be very large. So these things, typical dimensions here, I should have told you, typical dimensions here might be 100 angstroms to a micron, 100 to let's say up to a micron. So that it could be nano-sized objects, and the same for these. These could be larger. Okay. And you'll hear a lot about polymers, so I won't say anything more about them. Okay. But in the back of our mind, most of the things we'll be talking about, we have some solvent, and we're talking about things in the solvent. Okay. That's not everything in soft matter, but a lot of, I think most of the talks, many of the talks here will focus on that. I guess the liquid crystals might be neat liquid crystals. One thing that we should all have in our mind is solution thermodynamics. That's one thing that we have to bear in mind. And the way that I'd like you to remember it for these lectures is to think about dilute solution thermal. So I'm going to imagine a solvent where I put in objects. You could think of them, if you like, as objects like this, or smaller objects, molecules, and what I mean by dilute solution is that the concentration, C, is the concentration of objects. C is defined as the number of those objects I put in per unit volume of the material is small. And it's small in the sense that we're only dealing at this point with short-range interactions, short-range forces. And we'll get back to that later to see where it goes wrong. But for the moment, let's just so that the interactions are very short-range. That just means that they don't diverge at infinity. Then if we want to think of dilute solution thermodynamics, what we want to write down is the free energy. I'll write a free energy per unit volume. I'll just think of a homogeneous glass of stuff. Okay. As usual, I'm going to normalize the energy by temperature. T means, again, in all my lectures, T means KBT, and this is room temperature, or something like room temperature. In soft condensed matter physics, in contrast to solid state physics, temperature is often not a very useful variable. And the reason for that is that a lot of the parameters that appear are temperature dependent. So everything is temperature dependent, and it's not easy to learn much typically from the temperature dependence of objects. In solid state physics, you're usually working at very, very low temperatures, and the temperature dependence is typically more useful. Okay. That doesn't mean it's not useful here, but it's not a, and those of you who do experiments know you don't often vary the temperature. You vary other stuff. Okay, so let's look at the free energy per unit volume of a dilute solution of stuff. So the first thing is the pure solvent. If I have nothing, then the pure solvent, I'll call it F0 over T, is the pure solvent. And we're going to get back to that later. And then I can imagine just a power series expansion in the concentration. That's called a virial expansion. And I just want to copy it so I use the same notation. So there's a term B1 C, I'm just doing a power series expansion. A half P2C squared, 1/6 B3 C cubed, etc. Okay, this, I could do this formally, and right, these coefficients depend obviously on the stuff that I'm putting in and on the solvent. And then I have, remember, I have an entropy of mixing. So the entropy of mixing, I should write C log C minus 1. This is entropy of mixing. So for dilute solutions, I would write that, and this is called virial expansion.
So don't you usually include that in your heat term?
Q what?
The entropy of mixing, isn't it usually part of the Virial coefficients?
Not the way I do it, but maybe you can.
That's fine.
I mean, but you need a log. There's no logs here.
Okay.
You need a log. Okay, now, okay, so that's just a formal expansion, which you would expect would be okay as long as I have no long-range interactions. Just to get everybody on the same point, the chemical potential is how much is what you have to do, the work you have to do to add a particle. So the chemical potential for the solute, I'll just call it mu, is just the F, the N, and fix whatever things you want on the temperature. And you could see see what that is. It's in units of kT. It's just B1 plus B2C plus log C. Okay, that's just the chemical potential. The other quantity, and maybe I'll write it up here because it's important. The osmotic pressure. Osmotic pressure, everybody maybe should understand. It's, I imagine an experiment where I have a membrane here, permeable to the solvent, but impermeable to the solute. And I put some ahead of the solute. Here's only pure solvent, and it's the pressure on that membrane. Okay, that's what osmotic pressure means. I think again, well, everything I say you should know. In this language, I call it pi is C dF dC minus F.
I think that corner of blackboard is not visible from
Ah.
the level.
Thank you. So let's come back over here.
So are you going to elaborate on some of these things? Or
Pardon me?
are you going to elaborate on some of these things, for example?
What do you mean by elaborate?
Well, okay, where does that definition come from?
Yeah, I'll elaborate a little bit. Yeah. So let me first. I'll get to your question, but let me first write this down again so you can see it. I is C the F to C minus F. You could derive that just by differentiating. This is just thermodynamics, and in my language, it's C plus B1 B2 C squared over 2 plus 1/3 B3 C cubed, like that. Okay. Okay, so B1 is kind of irrelevant to the pressure. Okay. Now, question.
I'm trying to understand the last term of your Taylor series. I'm trying to understand the last term of your Taylor series expansion, and so that indeed you can expand also this logarithm and including the expansion and. Why is that important?
I don't know how to expand the log. I mean, C C is, it's not 1 plus C. C is small. So the log of a small number is big. I mean, I can't expand that. At this level, I can't expand that. That's why I had to keep it separately. Okay. I think that's, is there, am I doing something wrong? Okay. Now, okay, so this is just pure, if you like, phenomenology. Let's remember what the interaction between any kind of molecules is. If I look at the V of R between two,
You don't know what about coefficients,
I think I have all the coefficients right.
right? How about you take a derivative, don't you?
Huh?
Well, the common the third problem is superior, we have to take a derivative.
Well, if I take the derivative of the cubic term, I get a half, and a half minus a sixth.
It still gives you a half.
Yeah, I think it's right. Okay, so if I look at the typical intermolecular interaction, somebody says, between molecules, it always looks like this. Okay, that interaction between molecules always looks like this. There's some length scale here, A. There's some depth of a potential delta. And sometimes people write this like a Morse potential with exponentials, or those of you who do simulations always use the, what is it called? The 612 Leonard-Jones. Leonard-Jones, where this goes here as 1 over r to the 6th, and this goes as 1 over r to the 12th. This is Leonard-Jones. As we'll see, there's a good reason for this 1 over r to the 6th. There's no good reason for 1 over r to the 12th. It's just because 12 is 2 times 6, and it's convenient. There's no real, but so let's remember what this is. This part here, the steep repulsive barrier, which is quantum mechanical origin. By the way, I should say at the beginning that we're talking about the fundamental forces. The only force to a first approximation that plays a role in any condensed matter physics is electromagnetic interactions. That's the only thing you have to worry about. Strong interactions are in the background, they don't do anything. To a first approximation, the only thing that counts, I mean, you have to worry about strong interactions if you do neutron scatterings or something like that. But I mean, as far as the physics of what's going on is concerned, it's all dominated by electromagnetic interactions. Okay, and this hard core is just a Coulomb interaction where you're pushing electron wave functions on top of each other. It's just a Coulomb interaction between electrons, but it's quantum mechanical. So this is hard core. This part is a fluctuation force, which we'll talk about later. But the point is that all interactions between molecules look roughly like that. Okay. And so if you want to calculate, you could use, if you know the interaction between the particle, between the objects, then you could calculate these coefficients. Okay. And in particular, B2, which is called the second virial coefficient, and it's the first one that plays a role here in the osmotic pressure, is something like 1 minus e to the minus this potential, V of r over t, integrated over all space. And now where does that come from? That comes from taking this set of particles and calculating the partition function. There's a Hamiltonian, which is a sum of all these pairwise interactions. You assume they're pairwise. And you put that in the partition function, and you assume low concentration. You turn the partition function crank. It's done in all the textbooks. And you calculate the coefficients in this expansion. just this way, and you just match terms, and this is what B2 is, okay? Now, you have to be careful. We're talking about objects in a solvent. So this interaction is not the interaction between those objects in vacuum, it's the interaction between those objects in the solvent. So this interaction that I'm putting in here to calculate this B depends on the solvent. We have to remember that. We typically often forget that. It depends on the solvent. Okay. This is the interaction through the solvent. Okay. However, that's defined. Okay, but given that this is B2, the higher virial coefficients, B3 and B4, you could also write in this kind of structure, but they involve multiple length integrals, and they get increasingly messy and difficult to calculate. Okay. However, this one has a lot of simple physics in it. For example, if I look at this potential here, you could imagine several limits. If the temperature is much bigger than delta, delta is the depth of this minimum, then you see that this thing is always, V over KT is always small. E to the small number is 1. 1 minus 1 is 0. So this is 0 until, for any separations of these molecules, bigger than A. However, when this R is smaller than A, this thing that becomes very large. E to the large minus large number is 0. This is 1. So that means in this limit, B1 is of the order of A cubed and is greater than 0. A is this. Okay?
B2. B2.
B2. It's a volume. By the way, units, dimensions are important. You see, this is a volume, B3 is a volume squared. Okay. If T is small compared to delta,
Oh, sorry.
yeah,
You said units are important. It's a volume. So why is that important?
say that again?
You said units are important. It's a volume. So
Yeah,
why is it important?
because
It's a
this
volume?
is an energy per unit volume, so that's a C squared, this has to be a volume.
Right.
This has to be a volume. I'm just
Yeah,
pointing that out, what the dimensions are.
That tells. What does that tell me about that coefficient?
Well, okay, so let's look at B3. B3 I won't even write it down. It's a complicated integral that involves 3 particles. But because it's a volume, and the only length of this problem is A, you can write down immediately, this is of order A to the 6. Tells you that automatically. And in fact, we don't almost never worry about B3 because it's not very sensitive because it's a multiple integral. When you integrate, you smear out all the details. That's why the only one that's very sensitive typically is this one, B2. Okay, so if I come back, if T is less than delta, then I have E to a positive big thing when R is in this range where the minimum is. And that could be very big. So typically in this range, B2 is of order, it's a volume, has to be like A cubed, E to the delta over T. Negative, because of this minus sign. So if I made a plot of B2, I said what I wouldn't do before versus temperature. I treated this seriously, that delta was not temperature dependent, of course, which it is. You would say that B2, at some point it goes through 0, which you know in imperfect gases is called, I guess, the boil point. And in polymers, this is called the Flory point, Flory temperature. A lot of physics could be, for dilute solutions, as you'll see, and probably you'll see a lot more, can be thought of in terms of this virial expansion. Okay. Now, of course, we're not only interested in dilute solutions, but this is a good place for everybody to remember. Okay, so this is all stuff that we should know, I think. Okay. Okay, now, oh boy. Before, already at this level, we could see some of the effective forces in the problem that we're dealing with. Okay. So I hope that everything I said you've all seen before, or some version of it.
So Phil, does this imply some kind of collapse, or what is it?
So say that. What?
When B2 goes to change its sign, it implies some kind of collapse? Or?
Yeah, so when B2 when B2 becomes negative, that means you have effective, attractive interactions. The objects want to sit in their potential minima, and you have things, so that's a good point. So that's when we'd say that the solvent of this material, which is what determines that interaction, is a poor solvent. We would say when B2 is negative, it's a poor solvent. When B2 is positive, it's a good solvent. That's a good point. B2 is positive means the objects are effectively repelling one another. That means they want to be surrounded by solvent. Remember, this interaction is the interaction in the presence of the solvent.
Sorry, you still wouldn't have, would you get collapse at that point? Because you still have the entropy.
Yeah, so it doesn't mean it collapses, but it means there's a tendency to collapse, of course. Yeah, so what you say is right. Entropy, for a solution which is dilute enough, entropy always wins. If you put a hydrogen atom in the middle of the universe at a fixed temperature, it's going to ionize spontaneously because it's KT versus the binding energy, 27 electron volts of hydrogen. Okay. So entropy will always win if the system is dilute enough, and that's a message that we should keep remembering over and over again. That's an important point. So I'm glad you said that.
When people do simulations, they like modeling polymer in a good solvent, they oftentimes get rid of the attraction altogether, so just use the repulsive part of Lennard-Jones or something like that. Is that just because they neglect this attractive part of the potential, or can there be situations where the solvent mediates it in such a way that there's actually no attractive part?
Yeah, so well, maybe there's an expert here who wants to answer that, but I think it's just what you said, that if you're interested in the repulsive stuff, then you think you're in this region up here where you don't have to worry about the attractive part.
Sometimes we use just for the exclude volume interactions between the particles.
Yeah. So, is there anybody else
He's
want to add
referring to
anything?
WCA theory.
Yeah, it's a WCA.
Yeah, so you're referring to WCA theory, which is
That's
really
right.
for hard sphere systems. Right, so it's to try to see like what a G of R is for a hard sphere system.
Right,
So
can this be-
people use that beyond it, right? But that's what those positions were actually developed for.
Right, but is this just a model, or can there actually be a real situation where you only have an attractive part?
We only have say that again. We only have.
Where you actually have only an attractive,
a repulsive part.
of the potential zone.
Well, okay. So there are systems which approximate that. If you take there's a lot of people who in the colloid community take colloidal particles, like little spheres, and they put on polymeric hairs, short hairs, where the solvent is a good solvent for the polymer, so you're in the temperature much bigger than the delta for the polymer. And then the interaction between the spheres is, to a first approximation, hardcore repulsion. Now, you always have some long-range attractions, which we'll talk about later. But if they're small, if they're small enough, you can neglect it. But I mean, you never have a perfectly. At the end of the day, you always have attractive forces somewhere in the problem.
And you can do perturbative expansions about that too, right? That's part of why WCA is useful.
Yeah. Well, I mean, this is kind of a pretty big.
Yeah.
So based on the approximations you had, so why B2 is increasing as temperature increase? It seems it should increase when temperature goes down.
What? If you look at the fundamental interaction, things want to be stuck together. There's always attractive forces. And B2 positive means repulsive forces. So at the end of the day, the ground state of any system is stuck together. Everything stuck together. So B2 is increasing B2 is increasing repulsions. That's the way it's defined.
So does that mean it should be a negative sign in the exponential of the second one? Of the low temperature approximation?
There is a negative sign.
Okay.
You're right. It's negative because of this negative.
I thought it's an equal sign.
Okay, I'm sorry. No, it's a negative. You're right. It's a negative. I'm sorry. Okay, so good. Okay, so it's important that we kind of focus on this. So let me now. Already, just with knowing this stuff, we see some things that are important in soft matter. So let me imagine the following situation: that I have my beaker of stuff, and I have my solvent, and I have some small solute particles. I'll draw my little solute particles. You can think of them as little spheres if you want. And in addition, I put in some, if I had a different color here, I would use it, but I can't open it yet. I have some, a few big red particles. These are all, you should think of these as solid particles. So already, what you can see is something that's called a depletion interaction. This was first, as far as I know, mostly due to Osawa. Not so many years ago. This is not ancient. He's still alive. So just to give you this feeling. And the idea is the following: that there's an interaction between these red guys because of these little white guys. And the way that it works is the following. What did I do with my piece of red chalk? So let's imagine, clearly I'm thinking of these red guys as big, very big, and if two of them get close together, it's like two flat surfaces. So let me just think, let me look very close, and here's one red guy, here's the other one, separated by some separation, let me call it H. And let's think about what happens. And so the size of the white guys here, I'll call B. So think of the white guys as a sphere of radius B. The red guys as some sphere of some bigger radius, much bigger radius. I don't have to specify it here. And suppose H is less than B. if H is less than B, then these small guys can't fit. So that means there's a region here, this is a depletion zone. Okay. But if I look at the large scale, these guys, these feel an osmotic pressure due to the little white guys. There's a, if the white guys are very dilute, there's an osmotic pressure is CT. I already wrote it down. Here it is. Let's be very dilute so I don't have to worry about B2. But, so there's a pressure CT on this side, but there's no balancing pressure on the inside because the concentration is 0 in here, if H is less than B. So that means that there's attractive force between the red spheres whose range is something like B, and there's a pressure which is something like minus CT. Now, in other words, these guys are being squeezed together with a pressure, a disjoining pressure, using Derrida language, minus CT. Or the opposite of a disjoining pressure. They're being pushed together. Okay? And so already, whenever I have a solution of multiple components, which we're often dealing with, there's an attractive force between objects, just due to this. Okay, this is there all the time, and you always see it. Okay, so clearly, if you want the force to be bigger, you play with the concentration of the small guys. Okay. Now, so what I've given you is the crude picture. If you want to work this out better, and it's complicated, and you have to decide what it means for the red guy to be bigger than the white guy, what the conditions are, that's more of an exercise you could try to work out. That's like a homework problem. Okay? But the crude picture is that you have this kind of depletion. So you see that already just from knowing something about dilute solution thermodynamics, and it should be very well known, but it's not that ancient. And nowadays there's lots of experiments that rely upon that, mostly in colloidal systems. Okay, I'm supposed to go to what time? 10:30? Okay. Okay. So now, any comments about this? I'm not going to say anything more about depletion. I'm sure you'll hear about it later this week and next week. So you have your homework problem, how to work this out in detail, how to decide what if the red guy is 10% bigger than the B guy. Does it still work? That's a good question. Okay.
Could you put some numbers? What is H, for example? It's more than 1 millimeter?
Well, it depends on B. I said this is true if H is less than B. So suppose B is 1,000, say B is 100 say 10 nanometers, and A, the red one, is 100 nanometers. So the range is just given by the sizes of the objects.
So could you represent those forces by changing B2 for large particles?
That's a good question. That's right. So if you, okay, so now, that's a good question. So now, if you think of my solvent as the pure solvent plus the white colloidal guys, then if that's a new solvent, a two-component solvent, then this interaction could be represented, would be an effective B2 between the red guys. Absolutely. That is exactly the way you should think about it.
In the
Good.
same vein as that, if you just have if you just have one component in a solvent, and of course the solvent's going to have some finite size, so we normally.
No, it doesn't work quite that way, because the solvent is at high concentration.
Is it high?
It's not, I can't
So it's the,
describe the solvent by a virial theory. At least not obviously. That's the hard part, is that the solvent is dense. And so we can't use this simple way of doing it. And that's a good question, because that's a very important point. Because very often, and especially here where there's some emphasis on biological systems, the solvent is water. And water is a very tricky, complicated solvent. So we have to we can't just doing stupidly representing it by F0 like I do here doesn't do justice, because there's all kinds of effects on that VLR. And so we're going to spend some time talking about that at the end. Okay, but the thing is, I can't represent it by a virial expansion.
Sorry, what is the big right guy?
What is?
The big right object?
Another colloidal particle.
Okay.
Or another emulsion
So
dot.
it's different from the white little
It
guy?
could be made of the same stuff as the little one.
Okay,
It could be, it could be the same kind of stuff, just much bigger.
all right.
There was another question.
If you have say, a cluster of red big particles, does the depletion force disappears in the center?
I didn't hear very well.
If we have an aggregate or a cluster of red particles, does the force exist within the cluster or just at the frontier of the cluster?
I see what you're saying. The way I would look at it, it's like a pressure pushing in from the edge of the cluster. It's not a
Internal force.
yeah. This is the yeah. You're not allowed.
I'm not allowed.
Yeah.
Quick question is, how does that depletion attraction fall off that function?
Well, the way I talked about it, it's like a step
Yeah,
function.
right.
How it falls off in real life, I'm not sure. Does anybody know? Michael, do you know?
Yeah, it's geometrical property. How this overlap volume changes with distance.
Yeah. So, but it's. Is there? I can't describe it by a power law. Or
No,
anything.
it dies completely at some point.
Yeah. So it's pretty.
It's a section of a sphere in a plane.
Yeah. Excuse me. There was another question. Okay. Good.
Oh, no, I'll ask it.
Yeah.
I've wondered about this and I've never asked it. So let's say your big red sphere is with a colon. Let's say it's a polymer. Okay? And presumably we can say it has some well-defined size, some RG. Then the depletion attraction would happen for large solutes, you would think, that couldn't enter the polymer, but at some point it would die off if they could diffuse through the polymer. Is that
Yeah, I think that's correct. I think that's absolutely correct. And so that's right. If you have, that's right. I think that and that's a little bit of a tricky issue. Okay. So if I have, I don't know what to say about that. I think people have worked this out in the literature, though. I think you could probably find this about it. Or look at the case where my red sphere is not completely impenetrable, but has a certain permeability or something like that. I mean, they're clearly, the sharp division of something that's an impenetrable object is an idealization. And that's part of this is sort of an example of what I meant when I said that even the things that we think are easy that we should understand, you don't have to go very far before you find out that it become a little bit tricky.
So if you have polar repulsive spheres that are polar dispersed, can small ones precipitate or the large ones even though there's only pure repulsion? Same exact.
Say that again. Say
If
it
you
again.
have same chemistry,
material,
same
yeah.
material, some kind of polydispersity, can small ones, purely repulsive, precipitate or cluster large ones
I think so.
by just pure repulsion?
I think so.
Just the distribution.
I think so. I think so, but I haven't seen examples of it that way. But I think in principle it should work. Okay, so what I'd like to spend most of the rest of the time talking about is this stuff. This 1 over r to the 6th, the so-called dispersion forces. And this is a very, in some way, very simple, but another way, very complicated area. And so I'd like to give it to you. So I'd like to talk a little bit about it. And I myself don't understand all of the aspects of it because it's so complicated. Okay. But so I'll try to tell you the parts that I understand, and it'll be clear the parts that I don't understand so well. Let me. So let me. And like all of physics, we have to sort of. Part of it is lying, so I have to, or idealization. So I have to. I'll start off by lying to you a little bit, and then we'll fix up the lying. So I want to start at the most simple level. So let me start with our old friend, the hydrogen atom. Because I don't want any of this to be mysterious. And so I'm going to think of but I don't have to worry about all the details, so I'll be happy just with the Bohr atom. So remember that the energy for a hydrogen atom, I'll assume that mass of the proton is infinite a little bit, so that we have the kinetic energy of the electron, and then electrostatics. And here I should say, when I do electrostatics, I use CGS units. I'm using evil units. I have no epsilon, that's because I hate epsilon zeros and 4 pi. So if you need it, you have to supply the 4 pi epsilon zero, okay? Okay, everybody's happy with hydrogen. And then we have Bohr quantization, let's say Bohr quantization. I'm doing it, I don't have enough time to solve. Schrödinger equation is, I forgot what it is. Yeah, it's some integer n, 1, 2, 3 times h. Okay. H is Planck's constant. So this is quantum mechanics, got Planck's constant. Okay. So I just put this here. This is 2 pi r p is nh. So I eliminate momentum. I just remind you how to do Bohr atom, so that this effective energy looks like this. Looks like that. It's a minimum because I have this large centrifugal potential, 1 over r squared here. Okay. So for the hydrogen atom, you could all minimize that. The energy levels are given by something. I'm going to write it down just because m e to the 4th. M is the mass of the electron. M squared h bar squared. Okay, those are the energy levels, and the radii h bar squared over m squared. Okay, so those just come from doing this minimization. You've all done it before. The important things I have to remember is that this here for n equals 1 is something like 13.6 electron volts. We know all those numbers, M, E, H, we know. And this, for n equals 1, is about half an inch. Okay. So that's the solution for the ground 1s state of hydrogen. The important thing is this is huge compared to temperature, which is 1/40th of an electron volt. And this is isotropic. The 1s wave function is isotropic. If you want to, psi goes as e to the minus something like r over a. A is what, this is a. N equals 1. Okay, and I think you all know that. The important point is that the 1s state is spherically symmetric. And for me, this is a hydrogen atom. The hydrogen atom is the paradigm for all atoms. All atoms are the same. There are slight details in terms of orbital angular momentum, blah, blah, blah. But to a first approximation, they all look like this. Okay. So this is a spherically symmetric thing. It's neutral. So it has no dipole moment. The average dipole moment is 0 in the ground state, in the 1s state. We'll talk about the ground state. If I put this hydrogen atom in an electric field, it polarizes because there's a negative charge, there's a positive charge, the proton and the electron. And so it develops an average dipole moment which is proportional to the electric field. And I'm not worrying about, it's okay, just like that. If you want to put in vectors. Okay. In general, that's just linear response. And alpha, just remember, is called the polarizability. Let's get dimensions straight. So let's get the dimensions. Dipole moment is a charge times a length. The electric field, in my units, is a E squared, is a charge divided by a length squared, right? So the dimensions of this is L cubed. The dimensions of polarizability is a volume. Okay? For the hydrogen atom, there's only one length in the problem. That's the length. So you immediately know that this is of the order of A cubed. So the polarizability for hydrogen atom is something like its volume. By the way, it's exactly A cubed if you calculate it. But I mean, you see from dimensional analysis, it could be nothing else but A cubed times a number. Okay? Okay. Now, so let's think about this for the moment. So let's imagine that we have two hydrogen atoms fixed in space, separated by a distance r. So I have two hydrogen atoms. Here's hydrogen atom 1. Here's hydrogen atom number 2, separated by a distance r. So something funny happens. Because if I think of the hydrogen atom semi-classically, then I think of it as a proton with an electron whizzing around it. You could think of it that way. And that means that while the average dipole moment, the average over cycles, is 0, there's an instantaneous dipole moment that's rotating around like a lighthouse. Like a lighthouse. So at some instant of time, you would say there's a dipole, this one, moment mu1, pointing toward E, toward number 2. So that means there's an electric field at number 2 due to number 1, which is of the order of mu1 over r cubed. Dipole interaction goes as 1 over r cubed. Right? Just by dimensional analysis here. This electric field polarizes guy 2. So there's a dipole moment 2, which is E21 times alpha. There it is. Now, two dipoles interact with one another. So there's a dipole-dipole interaction, which is something like minus mu1 dot mu2 over r cubed. So this, let's plug everything in here. This gives minus alpha mu1 squared over r to the 6th. Now, the average value of mu1 is 0. We already said that. The average dipole moment is 0. But what comes in is the dipole moment squared. And what's the average of dipole moment squared for a hydrogen atom? Is EA squared. So there's an energy here minus E squared A to the 5th over R to the 6th. Okay, approximately. R to the 6th. That's R to the 6th. Okay. So this suggests that all neutral objects, hydrogen atom is just a paradigm for any kind of neutral polarizable objects, interact with a attractive interaction. There's always a minus sign, because both the pole interactions are always attractive. And it goes like this. Now, of course, it's very small. The A for hydrogen atom A is of the order of an angstrom. So clearly this is a weak interaction. It's not long range, it's short range. But it's always there. It's ubiquitous, that's what I meant by it. So all neutral objects have this interaction. Now, as I said, let me finish about my lying. So I lied to you. So where I'm wrong here is that I didn't take very seriously Maxwell's equations. Because even if I think of the semi-classical picture of the atom, where the electron is going around like a lighthouse, still it takes time for the signal the electric field to reach atom 2. That is, there's a retardation effect which I neglected. This calculation is right if the velocity of light is infinite. Okay. So this is not quite right. And it's right if the distances are very short. If r is very small, it's right, because then the velocity of light is effectively infinite. But if r is too big, then it's wrong. And if I do it with retardation, then this 1 over r to the 6th becomes 1 over r to the 7th, and then there's a c. And I'll get back to that later, okay? But for short distances, this is correct. Now, there was a question.
What about the other dimensions when you take two-dimensional system?
I couldn't hear it.
What about other dimensions when you take two-dimensional system, like between two surfaces, and one-dimensional, like before, and the Maxwell line?
Let's see. I don't. I think this is perfectly fine. I didn't use. I mean, of course, if the atom is constrained so that the 1s state it's not a, I take the hydrogen atom in 2 dimensions, then it's different. But as long as I take the hydrogen atom, the 3-dimensional, I mean, what's right is the following. What's correct here is that the dipole moment, the neutral object, I assume that there's a linear polarizability, and that I have, dipole-dipole interaction in 3D. Okay. But if you have confined systems, then if you have, say these were metals, say these were conductors, where the electric field was 0, and these guys were far apart, then this might be different. Then it would be different.
The interaction is logarithmic or...
Yeah, well, then it would be different, because then I would have to solve the Poisson, the Laplace's equation, and do that. So I would have a different, this R cube would be different. Okay, so that's true, you could have it. But as long as as long as this separation is smaller, that's right. Yes, right, so that's a good point. So this, I've really done this in infinite space, in 3D. Okay, so this is typical of what's called, this is a fluctuation force. This is an interaction that's associated with quantum fluctuations. This is quantum fluctuations. And notice, this is a T equals 0 calculation. There's no temperature here. Okay. So this is but such interactions always exist between neutral objects. So if we get back to the discussion a little before about can I have repulsive interactions, the answer is kind of no. Because we always have these long-range attractions. As long as the system has a polarizability, and every system has a polarizability.
Can you say something about the additivity of these type of forces?
Again, I couldn't hear it.
When we talk about electric forces and stuff like that, and we always have additivity. What is forces of this kind? What is the?
Okay.
Can I add up?
Yeah, absolutely. This is another. Okay, I told you I lied to you, so I didn't quite lie to you yet here. But this interaction, when we treat it here, we treat it like a potential as if it were pairwise additive. These interactions are not pairwise additive. You're absolutely correct. So if I was very careful to only talk about 2. If I have 3, the interaction between 2 is different because of the presence of the third. So this is a very tricky, delicate point. What we know from what we believe about Maxwell's equations, until that's proven to be not right, is that the ordinary Coulomb interactions are pairwise additive. But these are not. And you'll see that in a minute. So you're absolutely right. And that's that's why part of the reason I said these things are really complicated. Because you have to worry about this retardation that I talked about, and you have to worry about the fact that these things are not pairwise additive. So and those are the 2 things that make this stuff very complicated. And let's see that a little bit more specifically. So let me come over here. I like this. So let's see where that leads us. So let's imagine that I have 2 condensed materials, stuff with lots of atoms, think of solids. Separated by a vacuum distance d. Now, if I assumed that where's my red chalk? That this was composed of dense, like a solid, of atoms here and one here, that each one of these atoms interact with each other only through this 1 over r to the 6th kind of interaction. Then, if you forgot about the lack of pairwise additivity, you could compute the force between these two slabs, right? You just add them up. The way you do E and M, you add them up. You just integrate, and that's another homework problem for you to do that here. Assume that there's a density rho on both sides. Rho is the number of these red molecules per unit volume. And you could calculate the energy of interaction, and these are infinite. There would be an energy per unit area, right? So let me say there's an interaction energy per unit area. And we could figure it out by dimensional analysis. You say that it's this guy interacting with those guys, so this interaction should be attractive because all these forces are attractive. Okay. It should go as the square of the density, the number per unit volume. It should go, because they're adding up pairwise, it should go as the square of the polarizabilities of the objects. By the way, this is a number per unit volume, this is a volume, this is dimensionless. There's an energy scale of the interactions. You can see that energy scale here. The energy scale is given by whatever the prefactor of the 1 over r to the 6. I'll just call it an energy scale. Epsilon, which is an atomic energy. It's like E squared over A. It's like the energy of a hydrogen bond. And that's it. To get this as energy, to get the dimensions right, this has to go like D squared. So you could do that just by integrating. The way you integrate Coulomb interactions or anything, you can integrate with the 1 over r to the 6th, and you'll get, and there's a number here, and you'll get that answer. But this is just a dimensional analysis way of doing it. Okay. Okay. So this would be, this would say that there's you see why it's D squared, it has to have the right dimensions. Okay. Then the pressure, again, the joining pressure using Derrida language is just a derivative of this with respect to D, the negative derivative. So there's an attraction which is 1 over D cubed. Right? So that's assuming pairwise additivity, so I'm not worrying about this thing. And most of the time, this gives you a reasonable guess of what the answer is, most of the time. But not always, and we'll see now. Okay. Now, by the way, all of this stuff on these dispersion forces, if you want to look at more authoritative things, there's a relatively recent book by Adrian Parsegian. And there's another very good book older by Ninam and Mohanty. And if you want to see it in the most unpalatable form, there's Abrikosov, Gorkov, and Zhelezhinsky. Okay, that's in a horrible way. Okay, okay, so there's a lot of, okay, so how do we see where the problem is? Okay, so the way people usually write this is minus A over 12 pi. Don't ask me where the 12 pi comes from, D squared. And A has a name, it's called the Hammacher constant. It's an energy, and it's typically, if there's a solvent between, it could be something like a a few hundredths to a tenth of an electron volt. Okay? If there's vacuum between, it's more like an atomic energy, more like an EV. Okay. Okay, so now you can see that this, what I told you in some limits, is pure nonsense. No. And in the following way. I told you that the scale of the interaction is given by the polarizability, which is the volume. Suppose instead of hydrogen atom, my individual objects were little conducting spheres, metal sphere. What's the polarizability of an ideal conducting sphere? A radius A. A cubed. It has to be the volume. Okay. When I mean ideal conducting, mean where the electric field inside is really zero at all frequencies. I mean, I've been also solving about frequency dependence. So the polarizability of a small conducting sphere is its volume. So what if my two slabs are made of conductors? They're infinite. So the interaction is what? What's A? Infinite. So this says that if these are two conductors, there's something wrong with my calculation. The Hamburger constant should be infinite. And that's getting to your question of pairwise additivity. It has both that and retardation. So the problem is that this is too crude to look at that case. So let's look at that case where these are conductors. Because you can see there's something wrong here. Does everybody see what the problem is? You see the difficulty, that if these are metals, the polarizability of a conductor that diverges as the size of the conductor. And this, my two-body additivity calculation says that it has to go as the square of the polarizability. So it would be, if these are two metals, this calculation would give infinite. So this tells you that there's a problem. So this was fixed, I think, I don't know first, but the one I know first is from Lifshitz. Is he the first one that did this, right?
I think
From Lifshitz. And so let me, I'm going to sketch out very briefly the classical way to do this problem, which is not the way I like to think about it, but let's try to fix this. So let me imagine I have this problem, and these two stuff are conductors, where there's enough mobile electrons that they have screening, and the electric field inside the conductor is just the kind of conductor we talk about in freshman E&M, where there's zero electric field. Okay, so all of this stuff that we talked about is based on electromagnetic interactions. So if you want to think of two conductors with electromagnetic interactions, let's try to think about it. So the interactions come because of electromagnetic origin. Electromagnetism is exchange of photons. So we have, if we want to go to fundamentals, we should think of this vacuum here. This all is immersed in a black body radiation, and now we can even bring in temperature and say that there's this thing has a temperature T. Then we could write down that if I want to do this a la statistical mechanics, and I'm not going to do it, I'm just going to stretch it out, and there's a partition function, which is the trace of e to the minus beta times the Hamiltonian, 1 over kt. But in the case of a photon field, we know that the Hamiltonian is the sum over all modes of the frequency, the energy of a photon on a wave vector q. That's h bar cq in free space times times the Bose, NQ is just the Bose distribution. Okay. Bose-Einstein distribution. Okay. Let's see, NQ, just to remember, is 1 over e to the h bar omega q over t minus 1. Okay. Okay, so that's this describes photons in free space. This describes black body radiation.
Sorry, what's the second term?
This?
Yeah.
That's the 0-point motion a half. KT is 0. Okay, so remember that free energy is minus T log Z, the free energy of a black body system. I'm going to put in the boundaries later. Is just, I just put this in here, turn the crank. This is just a sum over Q of the logarithm of something messy. It starts to look messy, but it's not so bad. H bar omega Q over 2T. Okay. So this is the free energy of our system, but we have to remember that we have these conducting boundaries here, and the electric fields must be 0. So we have to solve the wave equation in here, and we have to make sure that the first mode that we have is that one. This is plane waves in a waveguide. Okay? Because that the electric field has to be 0 at the surface. Okay. So that means when I calculate this free energy of this system, I have to subtract out all of the modes that have a wavelength longer than 1 over d in that x direction, Okay, so you could do that, and you have all kind of divergences, but you can calculate the pressure is just minus the F dB, and you could just do this. I'll get the answer in a different way, probably at my next lecture. But this thing becomes, to a first approximation, minus h bar c. C involves h bar. It involves c over d to the fourth. Okay, that's doing this, and there's nothing special. You've got to make sure you take the derivative, because each one, this term diverges. So you've got to make sure you take the derivative. And that's what you get. No, nothing special, just arithmetic. Just calculate. You could do that for a homework problem if you want to. I have it done. It takes me maybe 2 sloppily written pages to do it. Okay? Replacing sums by intervals and things like that. Okay. So there's an interaction which is attractive. Let's compare that to this. It's attractive. The pressure is 1 over d to the fourth, not 1 over d cubed. It depends on h bar, but so does this, because h bar is hidden in the but this depends on C. Notice if I let C go to infinity, the velocity of light go to infinity, as I did here, I get infinite. So you see that part of the issue why this diverged was that I didn't take into account retardation. And also, I'm not doing it by pairwise additivity. I'm doing it as a field. So there's no pairwise additivity in this Lifshitz calculation. He's treating each slab as just a massive region where there's no electric field.
Is this basically what is called Casimir effect? One over d to the fourth is Casimir force?
Pardon me?
1 over d to the fourth is Casimir force, basically?
This is whatever you want to name you want to call it, Casimir. I don't know the right names. They're very technical names, or whether this or that, and for me they're all the same. They're all fluctuation forces, Casimir, Van der Waals, you call it whatever you want. I don't know what the true name is. So if you're a purist about names, don't ask me. But to me they're all the same. They're fluctuation forces. The purists worry about names, and I don't. Okay, I'm sorry. So I'm the wrong person. But it's that.
But is this really the same force in origin as what you were describing before? Because here you were describing the fluctuations of the space between the plates, but there you were describing the fluctuations of the
that's right. Good question. I think the answer is yes, but we'll say a little bit more. Now I've sort of run out of time, so I stop. So I'm going to say more about this Wednesday. I'll tell you. So I'll start from here Wednesday because I have a different way of thinking about this. For me, I'll tell you in advance. In fact, you can work it out as an exercise. For me, the way to think about this is to think of it as a depletion interaction. This is a depletion interaction where I'm depleting photons from the certain class of photons from the center, and then I have an osmotic pressure of photons, radiation pressure from the outside. And that's the way to think about it, and that makes it all simple. Okay, that's the Joe Embry way of thinking about it. Okay, that's why I didn't want to work this out. I'll get the same answer that way in a few lines, just by kinetic theory. Okay, so we'll continue at this point on Wednesday, and then we'll talk about it. Okay.